Hello and welcome back to Geometry. Today we are going off book to still cover section 2.5 and complete some notes, but we're doing things a little bit differently. The focus originally of section 2.5 is on the paragraph proofs as well as postulates regarding points, lines, and planes themselves, but I really want to focus in on this second part, justifying your answer. So our objective here today is not just to write proofs, but to use those postulates, theorems, and other properties to write proofs and justify our answers. This year we're focusing less on writing formal, structured proofs and merely using the ideas and concepts and structures of proofs in order to effectively justify our answers in mathematics. But there are some new vocabulary terms we do need to know from this section before we can get started. First, a postulate. Postulate is a new term. A postulate is merely a statement accepted as true without proof. It works as a starting point, much like we had to note the point, line, and plane were undefined terms that we couldn't provide a proper definition of because they served as the starting point for all our future definitions. Postulates serve as starting points for all of our future theorems. Speaking of theorem, a theorem is a statement or conjecture that has already, or could be, by exercise, could be proven. And what does that proof look like? A proof is a logical argument where each statement is supported by an established truth. That truth could be a postulate or a theorem or just a definition, but there is something that we all agree on that is true, backing up each new statement added by the proof. Within that proof, in fact, the majority of the proof, is a deductive argument. The deductive argument is a logical chain of statements connecting given information to what is being proven. So this will be the meat of the sandwich in your proof, as it were, with the outer layers being the given information and the final statement that you're trying to prove in the first place. Now, you have actually done this before in algebra. Here's an example of an algebraic argument. This is actually a type of formal proof. Here, this would be a two-column because we are writing all our statements in one column and all our reasons in the other. We're going to solve this equation for x and give a reason at every step. Starting with the original given equation, how do I know this is true? This was given to me. My next step, I can turn this 3 times the quantity 2x plus 1 into 6x plus 3 and so on by using distribution. So the reason I know this next line is true is I've used the distributive property, or you could put it in verb form to distribute there. Next, we will combine like terms to get our third statement. Then we subtract 12 from both sides. Again, depending on the teacher you had, you might write your reason as the process that you're doing, subtract 12 from both sides, or you might be citing the property such as the subtraction property of equality. And then we get down to 15x equals 30 after adding 5x to both sides. And then finally, we find that x is equal to 2, our final answer, but our final reason would be that last step that goes from the previous line to the last line, which was to divide both sides by 15. This is a deductive argument, and because it includes the given and the final proven statement, this is an entire proof. So let's look at the structure of the deductive argument, and this is what I want you to focus on writing every time you are asked to prove something, justify an answer, or provide a deductive argument for something. You will always, always, always start with the given information. Now, this could be restating explicitly given information from the problem, or you might make observations from a diagram. In that case, the information was given to you in the form of a diagram. You will first turn that into words or equations. Then we will connect ideas forming with our valid logical forms. We've learned two of those. They are the law of detachment and the law of syllogism. These serve as our connecting features. They are not the reasons of themselves. You will use these, but you're not going to cite them as the reason for any of your given statements. What you will cite are any relevant geometric or even algebraic properties, theorems, postulates, conjectures, or definitions. And you will use these as you go. I'll provide some examples so you can see a variety of ways to incorporate that citation into your sentence structure in a way that makes the most sense. And then finally, always end with your conclusion or final answer. In the case of the algebra example, we wanted to end with the x equals 2. Now, here is a geometric example. We are tasked with using the linear pair conjecture. This is a conjecture that says a linear pair of angles are always supplementary, and thus, by definition of supplementary, their measures will add to 180 degrees. And the diagram at the right, so notice the diagram provides us with some angles and names and numbers of those angles, to write a deductive argument explaining why angle 1 must be congruent to angle 3. Now, we already know a different reason why angles 1 and 3 are congruent. That would be the vertical angles. But this could serve as a proof for the vertical angles property. So first of all, from the diagram, we can observe that angles 1 and 2 form a linear pair. And if they form a linear pair, then the measure of angle 1 plus the measure of angle 2 will be equal to 180 degrees. That's that linear pair conjecture. We were asked to use it, so make sure that phrase comes up in our argument. And here I put it in parentheses as a citation, immediately following the statement that uses that. We also observe angles 2 and angle 3 form another linear pair. So measure of angle 2 plus measure of angle 3 equals 180 degrees. I don't need to say linear pair conjecture again because it's the same, using the same property twice in a row. Then by substitution, so now I'm going to use an algebraic property. Notice that I've created some algebra equations in order to invoke this. So I can substitute those two things are both equal to 180, so I will swap one side out for the other to get the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. Almost there. And for my final line, therefore, the measure of angle 1 equals the measure of angle 3 by subtracting the measure of angle 2 from both sides. Or we could have written this in reverse order. Subtract the measure of angle 2 from both sides to get measure of angle 1 equals measure of angle 3. Either order would be acceptable there. So there you have a full geometry example. What I have next for you is a partially filled in deductive argument. So I want you to try this yourself. Take a look at the diagram and pause the video. See if you can fill in these blanks to form the deductive argument in order to justify your answers for all three missing angles, A, B, and C. All done? Welcome back. Let's check your answers. From the diagram, we can see that angle A forms a linear pair with the given right angle. Since all linear pairs are supplementary, the measure of angle A must be 90 degrees. Next, angles A and B are vertical angles, and all vertical angles are congruent. Therefore, A and B are congruent. So the measure of angle B must be 90 degrees. Finally, angle C is complementary with the given 40-degree angle, so C plus 40 equals 90 degrees. Therefore, C equals 50 degrees by subtraction. Notice here that I've gone ahead and created the equation C plus 40 equals 90 degrees and done a simple subtraction as my final step, whereas earlier for angle A, I noted that the linear pairs are supplementary, but I did not create the equation A plus 90 equals 180 and subtract 90 from both sides. I've skipped a couple steps that I'm going to assume the reader following along would be able to do. You can get away with one or two of those if they are very simple like this. 180 minus 90 equals 90. We have done that many, many times. I encourage you when you're first starting, write out as many steps as possible. As we continue, we'll be doing a lot of similar steps all together, and you can start to chain some of those together and save a few of them. This is much like in algebra when you would add your constants and your variable terms to both sides of the equation at once, saving you a few lines. Here is example 2. Once again, go ahead and read through this problem, pause the video, try it yourself, write out your own deductive argument to back up your conjecture, and then come back and check your answer. Welcome back. Let's compare our answers. In each diagram, ray AC bisects obtuse angle BAD. Classify angle BAD, DAC, and angle CAB as acute, right, or obtuse. Then complete the conjecture. So in the first diagram, measure of angle BAD is 120 degrees. That makes it obtuse. And we can see BAC and DAC are both acute. In the second diagram, measure of angle BAD is 158 degrees. It is also obtuse. And the two smaller angles are both acute. And in the third diagram, the measure of angle BAD equals 92 degrees. This is a bisector. Half of 92 would be 46. So yes, BAD is obtuse. BAC and DAC are both acute. Following that pattern, we would make the conjecture: if any obtuse angle is bisected, then the two newly formed congruent angles are always acute. Now, let's justify our conjecture with a deductive argument. Knowing where we are trying to get to, could we go back, use our other properties and definitions to create a proof so we can be absolutely certain that every obtuse angle, when bisected, forms two acute angles? Here's what I've come up with. By definition, an angle measure, we'll call it variable m, is always less than 180 degrees. So m is less than 180. An angle bisector divides the angle in half. So half m is less than half times 180, or half m is less than 90 degrees. If the new angle measure is less than 90 degrees, then it is acute. Since this is the definition of an acute angle, I didn't need to cite that and say definition of acute angle. That would be redundant. If you're stating out a property explicitly, you don't need to say the name of the property or the relationship. All right, let's try one more. Here we have one dealing with segments and lengths of segments. This conjecture will be called the overlapping segments conjecture. Maybe that will give you a slight hint. As before, we'll start with a couple of examples, work out the lengths given, use that to come to a conjecture, and then try to justify that conjecture with a deductive argument. Go ahead and pause the video. Try this yourself. Welcome back. Let's compare answers. For the left side diagram, the length AC we can see will be composed of the length from A to B plus the length from B to C, so that's 25 plus 75 is 100. BD is BC plus CD, and that will be a 75 plus 25, also 100 centimeters. On the right side diagram, segment AC, that length will be A to B plus B to C, so 36 plus 80 more equals 116 centimeters. And BD is BC plus CD, is 80 plus 36 is 116 centimeters. I'm starting to see a pattern. So, I predict if any segment AD has points A, B, C, D in that order, and segment AB is congruent to segment CD, then segment AC will be congruent to segment BD. How could I justify that conjecture? With a deductive argument. Well, notice that we relied quite heavily on the diagram in order to visualize how all of these different segments and overlapping segments went together. If you're presenting this deductive argument to somebody that hasn't done the prior examples, they won't have the diagram to go off of. So as part of any deductive argument or proof, you could create a diagram as a visual aid. We actually could have made one up here, drawn in an angle, measure and labeled it measure M, and then the two divided angles as half M's. So I'm going to make that explicit here and start by insisting we draw segment AD with points A, B, C, D in that order, with segment AB congruent to segment CD. It would look like this, or could look something like this. And now I can reference those lengths much easier. So the rest of the argument follows. By segment addition, we see that length AC equals length AB plus length BC, and length BD equals length BC plus length CD. Since AB equals CD, that was given as the congruent segments above, but by definition of congruence, the lengths are equal. We don't need to say that every single time. By substitution, AC equals CD plus BC. So notice the change that I did in that single equation above and below, which means AC equals BD by the transitive property of equality. So I already said that AC equals CD plus BC, and BD equals BC plus CD. Transitive property, if you recall, if A equals B and B equals C, then A equals C. Or you could have also used another substitution step. Either one could technically work here. So I did include an option there in parentheses. And now that I've said length AC equals length BD, I can finally conclude, therefore, segment AC is congruent to segment BD. And this last step, though I just said you don't always need to write out why the lengths are equal because they are congruent, or they are congruent because the lengths were equal by definition of congruence, you do need to end with what you are trying to prove. And so since the way I wrote my conjecture was with segment congruence, it is best practice that I end my proof with the statement in the form of segment congruence instead of just leaving it as the lengths there. That will do it for this section from 2.5 on writing paragraph proofs and justifying your answers. So long, farewell. Enjoy the rest of your day.